Alright, let's get started. It's been a minute since we met, so let's do a quick recap as to what we are talking about. So, one of the main things we were developing all this first order logic for is it gives us the language and the framework for constructing axiomatic systems. That's largely what it's all about. We're out to construct axiomatic systems. That's pretty much what we use to encode bodies of knowledge. When we talk about some systematic body of knowledge, it's encoded in some axiomatic system. That's what we use. And so, that's largely the point here. We've been looking at some simple axiomatic systems. We did one for weak preference. We did one for group theory. The next one that the author introduces is one for arithmetic, which is what we'll be doing today. So, one of the points is, once again, give you another axiomatic system, get you comfortable with axiomatic systems. The author had a second agenda in introducing arithmetic here. He's also introducing the notion of informal proofs. Doing our proofs completely formally gets kind of tedious, and you notice that there's a lot of repetitive steps that we repeated over and over again. And so we're moving now to informal proofs as opposed to formal proofs. And so it's another example to just see a bunch of now informal proofs. Because with formal proofs, you have all the rules for exactly how you should do it. With informal proofs, there are no rules, and there's largely style, there's largely taste, there's largely what you like to do and what you don't like to do in constructing your proof. And so it's harder to get comfortable with informal proofs. Well, I don't know. I think it's harder to get comfortable with informal proofs than it is formal proofs for that reason. So probably the best way to get you comfortable with informal proofs is to just expose you to a ton of them. So that's largely what we'll be doing today. So with that, let's really quick recap the basic components of an axiomatic system. What are the components of an axiomatic system? What does it have?
Your axioms.
The axioms, okay.
Your undefined terms.
Your axioms, your undefined terms.
Your theorems.
We also call these primitives, just to help us keep clear in our mind. In logic, when we talk about a term, we meant a variable or a constant or combinations of variables and constants together with operators. But here when we say undefined terms, we just mean the symbols that are not symbols of first order logic.
Yep.
So I'll try and use the language primitives just to avoid confusing you about what we mean by terms. And we'll keep using terms to refer to constants, variables, and combinations of them with operators.
All
right.
Have your definitions.
Your definitions.
And then your theorems.
And then your theorems. Okay, so intuition, using high-level language like we're talking to a fifth grader, what would we tell them our axioms are?
There are statements that you just assume.
They give meaning.
Yeah, there are starting assumptions, there are starting statements. And then theorems are looking at the logical implications of all those statements. They're looking at, if the axioms are true, what else must be true? Those are the theorems, the things that follow from the axioms. Now, what are our primitives? These are the symbols that show up in our axioms that are not symbols of logic. They are undefined symbols. It is not defined what these symbols mean. How they get their symbols, or how they get their meaning, is from the axioms. The axioms give it meaning. Going back to a common example from geometry. Point, line, and plane are undefined terms, or primitives, in geometry. What's a line? What's its definition? I don't know, but it for sure has 2 points on it. I know that. What's a point?
Like principles again.
Yeah, I don't know, but there's for sure 3 of them that are non-collinear in a plane. I know it for sure has that property. And so the axioms give meaning to our undefined terms, so they're not meaningless. And then finally, we have definitions, which are taking our undefined terms and constructing new terms, new words that we want to use in talking. And all our definitions are ultimately exposable. We don't need them. They're simply a convenience to have. We can always and forever simply use our primitives in everything that we do in the axiomatic system. You don't have to have definitions. They're nice to have. They're combinations of these types of symbols. So with that, let's jump back to arithmetic. So, starting now with arithmetic. Again, so our 2 operators that we're talking about in arithmetic are times and plus. So let times and plus be closed operators on R. R here is going to be our domain of objects. The real numbers is what that fancy R means. But for now, pretend you don't know anything about the real numbers. So this is just a set of some objects in there. We have no clue what's in there. What do we know? We know that times and plus are operators on R. Meaning if I take two things in R and I plus them together, whatever that means, it spits out something else in R. Or if I take two things in R and I times them together, it spits out something else in R.
Is that closed in the topological sense too?
No, sorry. A closed operator is just an operator that takes members from the set and returns a member in that set. There is a notion of an operator that takes members of a set but can return members not in the set. Subtraction is not closed on the natural numbers because 2 minus 5 is -3, which is not a natural number. The natural numbers are 0, 1, 2, 3, 4, 5, etc. So, but it's pretty much what you mean what you would have guessed if I said that these are operations on that set. So let times and plus be closed operators on R, and let the less than symbol be a relation on R. Now, what's a relation?
It's a two-term predicate.
It's a two-term predicate. It takes two things out of R, and it spits out true or false. An operator takes two things, well, not necessarily two, it could be 3, could be 4, but these ones both happen to take 2. So something like plus here takes two things out of R and spits out something else in R. So relations take two things, spit out true or false. These operators take two things out of R and spit out another thing in R. Difference between operators and relations. So arithmetic, so let times and plus be closed operators on R and let less than be a relation on R such that it satisfies these 15 axioms. And now we'll go through each axiom. So axiom 1. For all x, y, and z, it's understood that when we say for all, we mean for all in that set. This is the domain that we're talking about. Everything comes from that set R, whatever that thing is. So for all x, y, and z in R, x plus y is equal to y plus x. Whatever the plus symbol means, it has this property. Similarly, for all x, y, and z, x times y is equal to y times x. Really quick, just looking at this, let's start talking about some of the primitives we see showing up. What are the primitives that show up in axiom 1? Plus. And equals, right?
That's a lot of
Wrong. Equals is now a symbol of logic. Remember that we are in propositional first order predicate logic with identity. So we can use the laws of identity, and we don't need arithmetic to give us our special rules for how we're going to use equals. Logic already did that. Arithmetic doesn't need to do that for us again. Every other symbol here are just symbols of logic with the exception of the plus and the plus, or the times and the times here. Right? Continuing our merry way. Tell me what these properties are called. Commutativity. This says addition's commutative. This says multiplication's commutative. You can swap the order, it doesn't matter. Next one we call associativity. For all x, y, and z, if I add the x and the y together first, then I add the z. That's the same thing as adding the y and the z first, and then adding the x. Similarly for multiplication. So addition and multiplication are associative, is what axiom 3 and axiom 4 say, giving you the higher level language. Okay, next one. This one tells us how to combine addition and multiplication together. What happens when you get a line that has both these symbols? What do you do with it? So for all x, y, and z, x times y plus z is equal to x times y plus x times z. Now so far what I have written here is nonsense, strictly speaking. And I have to have my parentheses here. Because that operator takes two things, right? I can't just have a times, a plus, a times, all these operators randomly. Each one takes two things. I need to specify how I'm doing this. So we're multiplying those two together, then that spits out one number. We're multiplying those two together, then that spits out one number. Then we're adding two numbers together. Go ahead.
Then is PEMDAS just something that's like introduced?
It's just a rule of thumb to help you understand some conventions.
Right, which I feel like we've all kind of gotten used to and just started to like.
Right, so always and forever, parentheses show precedence in terms of how you should carry things out. Outside of that, there has to just be understood rules. And so I am not going to put parentheses around every time that we do multiplication. And so right now, you and me are coming to an agreement that it's understood that anytime you have times and plus first, or anytime you have times and plus in some order, we're always going to do the multiplication first. And so I'm never going to write those parentheses.
So it's 100%.
So it is completely, strictly speaking, this is nonsense. But we're lazy. And so we're going to speak some nonsense. We're going to be less precise.
Yeah.
And it's just an understood convention. So we're getting lazier and lazier as time goes on so that we can write less and less symbols and still communicate perfectly. Right? So that's an agreement that we just came to, and now I no longer ever have to put parentheses around it, and you already know, oh, you multiply, then you do the addition. There's no rule that says that. It's just a convention that we all agree to adopt. Okay. Or if there's a rule that says that this is a rule, if we had put them there. Okay. Next one. Axiom 6 says that there exists something out there. I'm going to call it 0. Completely made up. I'm using that symbol to represent it. There exists that thing in R, such that for all x in R, when I add x with that weird thing, it just returns x. The high-level language for this is that there exists an additive identity. That's the thing, such that when you add it with anything, it returns identity, the exact same thing.
Is 0 an undefined term here?
So 0 is now a primitive. So far, what are our primitives? That we've come across. We come across plus, we come across times. Now we've come across 0. There's another primitive.
Okay, and that's supposed to be from group theory, yeah? The additive?
No, this is a completely different axiomatic system. You just see how group theory encompasses a chunk of this. It's like a small bite-sized chunk of this. And because that same chunk shows up in a bunch of different fields of math, we now have what we call group theory. Because it turns out very similar things keep happening in these axiomatic systems that we're interested in. So yeah, you already saw something very similar with group theory. Next one says, there exists something out there, we're going to call it 1, such that for all x, x times 1 just gives you x. Or in other words, there exists some multiplicative identity. When you take something and you multiply by it, you get back identity, the same thing. So now, there is another primitive. Right?
Yeah.
Continuing on our merry way. This one says, for all x, there exists some y, such that x plus y equals 0. No matter what number you choose, I can always find some other number, such that when we add them together, we get the additive identity element. High-level language that says every element has an inverse element, an additive inverse. Something that gets you back to identity. This one says for all x, if x is not 0, then there exists a y, such that x times y equals 1. Or in other words, every non-zero element has a multiplicative inverse, is how we would say that. For any x you choose, I can always find a y such that their product is 1, as long as the x you choose isn't 0. 0 has no multiplicative inverse.
Can we go back to axiom 8? You said it goes back to its identity. I didn't understand.
Pick any number you choose.
I understand that part.
I can always add some other number to it that gets us back to the additive identity element.
Additive identity element is
So we call that an additive inverse of x. The additive inverse is what you add to get back to identity. The multiplicative inverse is what you multiply by to get back to identity. The multiplicative identity.
no.
So to just be concrete, the additive inverse of 3 is negative 3.
I get
The
you.
multiplicative inverse of minus 37 halves is minus 2 37ths.
So I understand that fully. What I'm asking, take for instance, in axiom 7, you says x times 1 gets you back to its identity.
Get you, oh, did I say identity here? I meant the identity element.
The identity element.
Yeah, 0 is the identity element for addition. 1 is a This is the additive identity element. This is a multiplicative identity element.
Okay.
It's functioning the exact same way E functioned in group theory. Well, 1's not the exact same, but close to.
So you said 0 is the additive identity element and 1 is the what?
Multiplicative identity element. So each operator has its associated identity element in there.
Okay. So axiom 6 identifies 0 as the identity element. And then we're saying, hey, if you do x plus y, then you can get back to x's identity element, which is
The additive
defined
identity
by
element.
axiom 6. Okay.
Yep, get back to that thing we talked about in 6.
Okay. That's all clear.
Perfectly correct. Okay. Now, the next chunk of axioms are going to tell us about this relation. So those are the ones that tell us about the operators. The next ones are going to tell us about our relation. Our axiomatic system only has one relation, less than. So now that is our next primitive, our next undefined term. This one says for all x and y, if x is less than y, then it is not the case that y is less than x. If x is less than y, then y is not less than x. Next one, for all x, y, and z, this one just basically says less than is transitive, to use a high-level language. But for all x, y, and z, if x is less than y and y is less than z, then x is less than z. Next one, for all x and y, if x and y are different, if they're not the same, then either x is less than y or y is less than x. Next one says, for all x, y, and z, if x is less than y, then x plus z is less than y plus z. So if x is less than y, you can add the same thing to both sides and it doesn't change the inequality. Finally, for all x, y, and z, if z is positive and x is less than y, then x times z is less than y times z. Or in other words, if x is less than y and we multiply both sides by a positive number, we haven't defined that yet, but that's what we're going to be saying. If x is less than y and we multiply both sides by a positive number, it doesn't change the inequality. Or we multiply both sides by a number greater than 0. Good? And then finally, the non-trivial property, which is that 0 and 1 are in fact different numbers. They're not the same. Okay. So, quick recap. So R here is our domain of individuals. What do we know is in R so far?
0.
I know that 0 is in there. I know that 1's in there. Do we know anything else is in there yet? Not yet. But I know that this plus symbol is closed on the real numbers.
Yeah.
Which means if I add two things in here together, I have to get something else in there. Right?
Yes.
So let's look at 1 plus 1. That's something in there. That's something in there. Therefore, their sum has to be something in there.
Yeah.
Now, maybe 1 plus 1 is really 1, or maybe 1 plus 1 is really 0. And so maybe when I add those two things together, I get that, or I get that. Maybe I don't get anything new by adding those two things together. So we did this proof last time, but it's okay to do it again. We'll do a quick proof that 1 plus 1 is not equal to 1. It's in fact something different.
Oh, okay.
So let's prove that. So 1, assume by way of contradiction that 1 plus 1 is equal to 1. Okay, if 1 plus 1 is equal to 1, what do I know?
See, well, you know. Well, you know 1 plus 0 is equal to 1.
True?
That 1 equals 0.
Now how am I going to get there? I somehow need to subtract 1 from both sides.
We don't have to.
But we aren't even close to defining subtraction yet. So we got a long ways to go. But what's the axiom that ultimately is going to give us subtraction information?
The axiom 8 right there.
Axiom 8 says for any x you pick, anything in there, 1's in there, there must exist some other thing. We don't know what it is, but there is something in there, such that when you add it with x, you get 0.
Yeah.
So, 2, there exists y in R I don't know, we need to say in R. We're always in R. There exists y such that 1 plus y equals 0. I know that from axiom 6. Or sorry, axiom 8. Axiom 8 says for any x there exists some y such that x plus y equals 0. So there must exist some y out there such that 1 plus y equals 0. Okay, 3. Then, adding y to both sides of this, I get 1 plus 1 plus y is equal to 1 plus y. How do I know I can add 1 to, oops. Can't just go around putting my parentheses wherever I want. Have to do it correctly. So I'm adding y to both sides, so this addition has to happen first, because that's what was already there. So, then I know 1 plus y is equal to 1 plus y. I added y to both sides of that, whatever that y is. How do I know I can add y to both sides of that?
Isn't that a law of logic?
That's a law of logic. It's more foundational than arithmetic. There's nothing in arithmetic that we can use to derive that fact. It's from logic. We show that for any operations you have, if A is equal to B, then A circle C is equal to B circle C. As long as it's defined in your domain and circles any operation you can think of. Works for plus, works for times, works for function composition, works for matrix multiplication, whatever it is we're talking about. Works for differentiation.
And it's deterministic.
And it's defined.
Is that the same thing?
Are you saying that 1 divided by 0 is not deterministic?
I'm saying the operator has to be deterministic.
It has to be defined.
Meaning it has to output the same thing. If the same one input has to be the same output.
Oh, that's part of being well defined. We haven't gone to the theory definition yet, so we'll probably be doing that next week. Okay, so then 1 plus y is equal to 1 plus y. Now what can I do?
Use your substitute.
Yeah, I know that 1 plus y equals 0, so I want to replace this with a 0, and I want to replace this 1 plus y with a 0.
Which you do.
But I don't have this 1 plus that y. That one's added to this one over here. Very annoying. But we have associativity, which says we can move the parentheses over. Rather than having them here, I can shift them like that. So I can shift those parentheses over. So that gives me that 1 plus y is equal to 1 plus y.
Okay, and you're doing informal proofs now. Is what you're doing.
Yes, this is all informal. And so we know we could do that. That was using axiom. I'll often just tell you what I'm using rather than writing it out. That was using axiom 3. Now, this is the same thing as 1 plus 0 is equal to 0. What did I use there?
You just substitute.
Associativity.
Law of identity. Equals maybe substitute for equals is the mnemonic we use. Since 1 plus y equals 0, 1 plus y equals 0, 1 plus y equals 0. And then finally, what is 1 plus 0? How do you know? By definition, or by axiom 6 here, it says anything plus 0 is just that thing. Something plus 0 is just that thing. So I get 1 equals 0.
Which by axiom 15.
Which contradicts axiom 15, which says 0 is not 1. We got 0 is 1, 0 is not 1. Contradiction. So 4. Therefore, one plus 1 is not equal to 1. And now we could also do a proof to show that 1 plus 1 is in fact not equal to 0. We're not going to do it. But if it's not 1 and it's not 0, it's something new. And so 1 plus 1 is in fact a new number. And so we gotta come up with a definition for whatever that number is. And we just write a squiggly and jag out a line. Just making it up. And we say we're going to define that symbol to mean 1 plus 1, whatever that is.
Thanks to our friends in Arabia.
And, well, I think that these numerals come from India, but is it just the base 10 since that comes, or is it also the numerals?
They
gonna say, I think
invented
probably
the entire
started with
algebraic system, and I think the numbers and symbols as well.
Yeah, I think numbers went right there. Not sure.
Like 95.
Doesn't really matter, but if I had to bet $5 on it, I'd say India. I know they did a lot of algebraic work, which is why we labeled, but don't they even say like the algebraic, don't they have like a combination of algebra and India in the numeral name? Doesn't matter. Okay, whatever it is. And then we can do something similar now. So this is our new thing that we now know is in there. So we know there's this thing in there. And so if that thing's in there, then 2 plus 1 has to also be in there. And so we can go through the work of showing that something different. And so we get this symbol. And this is what we mean by 2 plus 1. And this symbol is what we mean by 3 plus 1. And we can go on our merry way, dot, 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 dot. Okay, now we know all the natural numbers are in R so far.
How do we know that we can recursively define this?
You would use strong induction to show that it's always something new.
Is that something that we know how to do?
Yes. Not in this class. We have not gone over inductive proofs in this class. But you could always show how adding the next one on makes the previous one without the one equal. So in other words, if 2 equals 3, then 1 equals 2. But we already showed 1 isn't equal to 2, etc.
So is inductivity a thing of logic then?
No. In this context, it would come from the ordering principle. Or we won't worry about it. Sorry, not going to worry about it. Because we're still missing one very telling axiom that we need to complete the axioms on the rails.
Very good.
The completeness axiom. But we're not going to touch that because it's hairy. So this is almost all the axioms on the rails. They're what we need to do basic algebra. Arithmetic. Okay, so we can go on our merry way defining all these numbers now. Hooray. Right? And so we now know that those numbers are at least in the real numbers. So 0, 1, 2, 3, 4, all the way counting up are in fact real numbers.
How do you define what symbols you use for what number?
For a what?
For what number? Like how?
It's arbitrary. We come up with some convention that we're going to do to list out the numerals. And so whatever the ordering is that you place those numerals in that this indicates, we have some system for doing that. And you know that after this numeral, we're just going to go to this. We have what we call a base 10 counting system. And we're pretending that that's a new symbol. And we go on our merry way.
So we don't like define the base 10 system in our arithmetic?
No. This system of arithmetic doesn't care whether you use a base 10 counting system or a binary counting system. I could have replaced that rather than doing 2. I could have done a 1, 0 just like that and done the exact same thing. So, doesn't matter. Okay. So, I think that kind of covers what we largely did last time. Oh, I also did the proof that 2 plus 2 is 4. Should we do that one really quick? So now, with our definitions, we can now do a quick proof that 2 plus 2 equals 4. Let's do it really quick. So 2 plus 2, what does that equal to? By definition, what's 2?
1 plus 1.
By definition, 2 is 1 plus 1. So this is equal to 2 plus 1 plus 1, 2 plus 2, right? Now I can use associativity to move my parentheses like that. So this is equal to 2 plus 1 plus 1. But 2 plus 1 by definition is 3. So this is equal to 3 plus 1. But 3 plus 1 by definition is 4. And so there we go. 2 plus 2 is 4. Alright, so now let's start the actual theorems that we're going to go through proving here. Our first theorem is that only 0 acts like 0. Okay, so what we're going to call theorem 1. Theorem 1, we are going to prove that for all x, y, and z, that, oh, I don't think I need a z. Don't need the z. For all x and y, that if x plus y equals x, that implies y must be 0. So I know that 0 has this special property, that when I add it with anything, I just get back that thing. But maybe some other number does as well. Maybe when we were generating along, as soon as we got to 1039 whatever, that number also had that property. How do we know some other number doesn't eventually get this property again? You guys aren't used to modular arithmetic, but this kind of happens with modular arithmetic. So we're going to show that that in fact doesn't happen, and that 0 is the only number with this property. Okay, now I'm going to force you guys to start kind of walking me through the proofs. Now we're kind of getting back into it. So here's what we're trying to prove. What's my first line going to be?
We're probably
Assume the antecedent. So here's our antecedent, here's our conclusion. We're trying to show if this is true, then this is true. So let's assume that this is true, so that implies this is true. So we can say assume x plus y equals x, or let x plus y equal x. Doesn't matter the exact terminology we use there. So let x plus y equal x. Okay. What am I trying to show? I'm trying to show that y is equal to 0.
Yeah.
Let's come up with an approach really quick. How might I get y equals 0 here? What in high level language am I trying to do?
You could try and like subtract x from both sides.
Yeah, I somehow need to subtract x from both sides, which we don't have yet, but we have the axiom that's ultimately going to give us that.
Oh, yeah.
So axiom 8 tells us,
Y is 0.
so then there exists, pick some symbol, doesn't matter what we call it. I'll pick w, such that x plus w is equal to 0. Not by axiom 8, right? Okay, so then what should we do? Let's add w to both sides. Just using, again, logic. So then w plus x plus y is equal to w plus x, just trying to be consistent here, right?
Yeah.
Adding the same thing to both sides. Okay, now what can I do?
You can associate.
Associativity, move these parentheses over. So then I get w plus x plus y is equal to w plus x. That was using associativity. Is that A3?
Yeah.
Okay.
Now you can substitute 0.
Can't substitute 0 yet, Mr. Fast and Loose.
Oh, you
yes.
guys switch symbols in the wrong.
Yeah, we got the wrong order there.
Oops.
We got to use commutativity first and swap the order of the w's and the x's.
It's going to be exactly.
So now we know that x plus w plus y is equal to x plus w.
Yep.
And that was using axiom 1.
Yep.
Yeah.
Now what?
Now we can substitute.
Now we can substitute for 0. And so 0 plus y is equal to 0.
I think we have to.
Which gives me, you need a couple more here, so I'll continue here.
I think we have to use commutativity again.
Commutativity again, we gotta swap the order on the y and the 0 there. So that gives me that y plus 0 is equal to 0.
And then that gives you that y.
And then finally, what is y plus 0?
Y.
Anything plus 0 is just that thing. So y plus 0 is just that thing. So y plus 0 is just y is equal to 0.
And we call that the identity element.
0 is the additive identity element. We have 2 identity elements, one for each operator.
That's right.
Good?
Yep.
All right, that wasn't too bad. On to our next theorem. For all x and y, if x is not 0, x times y equals x implies y is 1. Okay, so same thing with multiplication. So theorem 2. This is for all x and y, if x is not equal to 0 and x times y is equal to x, so those two things together imply y must have been 1. So this proof said there's only one thing out there that functions like 0. This says there's only one thing out there that functions like the number 1. 1 is the only number that you can multiply by to get back your same number again, as long as the number in question isn't 0. So if you find a number out there, y, that does this, then the y you chose was 1. That will always be the case. If you find one that does it, then it must have been 1, since it's the only one out there. All right, so this is going to be very similar. How do we start this? Yeah, so let x times y equal x, where x is some number other than 0. Now what do we want to do? Right, your junior high kid is going to say, we want to divide both sides by x.
Is the law that you can add any operator on both sides of the equal statement, could that operator also be an operator that removes from both sides?
I mean, sure.
But
In a sense, subtraction is removing from both sides.
Never mind. This actually doesn't apply to the situation. Just okay.
Okay, so we've got this. Now we want to divide by both sides, but we don't have division as an operator yet. We have to define that. The only operators we know are plus and times. But what's the axiom that ultimately is going to give us division? It's the one I'm standing close to.
Nice.
The one you're looking at. Oh man.
It's 9. For all x where x is not equal to 0, there exists a y such that their product is 1. Right? This is the one that tells us subtraction. This is the one that's going to tell us division, basically. Okay. So, 2. Notice that x is not 0. So this says as long as x is not 0, there exists something out there such that when you multiply x by it, you get 1. So, then there exists, doesn't matter what symbol we use, I'll use z this time. There exists z such that x times z is equal to 1. And again, that is from axiom 9. Right? Okay, now what?
Times both sides by z.
Yeah, times both sides by z. Multiplying by z is somehow dividing out x.
Yeah.
Right? So, 3. Just to make this concrete for you, if I've got 3x equals 9, and you're trying to solve that, you know, divide both sides by 3. What we're saying is multiply it by 3's multiplicative inverse, or in other words, multiply both sides by 1/3. That's what we're doing up here in symbols.
Yeah.
Rather than dividing by 3, we're multiplying by 1/3. 3's multiplicative inverse. The thing such that when I multiply 3 by it, I get 1. So z is the thing such that when I multiply x by it, I get 1. If x is 3, z is 1/3. Okay, so then there exists z such that this happens, so then z times x times y is equal to z times x. Multiply z to both sides of that, right? And now, using a bunch of commutativity and associativity, I'm going to rewrite that as x times z times y is equal to x times z, using both associativity and commutativity. So that was using axiom 2 and axiom 4.
Associativity is
Axiom 4 for associativity.
oh, for multiplication, sorry.
Yeah. I always debate combining addition and multiplications, associativity, and commutativity into one axiom.
You can do that into one.
Yeah. You just say for all x and y, this happens, and you just put an and symbol there. It's still just a statement, anding two statements together. Just makes referencing it easier. Okay, so we got there. Now what?
Axiom 7.
Well, not yet. What's x times z? 1. So we can do our substitution now, right?
Yeah.
So I'm going to do by substitution and use some commutativity and say that y times 1 is equal to 1. So we used identity, but we also used, identity and we also used A4 for commutativity. Okay, and now what's y times 1?
Is y.
Anything times 1 is just that thing. So I get y then is equal to 1. And that's using axiom, I lost it, help me, axiom 7. And we're done. Okay. Next one is our left-hand cancellation law for addition. So theorem 3, this one is for all x, y, and z, if x plus y is equal to x plus z, that implies y equals z. So we can cancel out the same thing on the left-hand side of an expression.
Isn't that, that feels like it should be a logic thing.
No, logic is you can insert it in there. Removing it is a whole nother beast.
Really?
Yes.
Nice.
Because it's you're removing a term from an operator. That's why I made it realize, yeah, you can't use a law of
To
logic.
get left-hand cancellation, your axiomatic system needs to at least be strong enough to get group theory in there. Well, I probably shouldn't say that, but
Why is that not a law of logic? It feels like it should be something that's logic.
because your system doesn't necessarily have some operator that cancels things out.
Well, if you look at x and y as just inputs into the operator plus, you're basically saying remove one of the terms from this operator, the plus operator, which is very bizarre than just adding more terms with an operator to both sides of an equal sign.
Definitely doesn't fall from logic for free, because then you want to assume that there's some counteracting element, some inverse element almost is what you're looking for. Something. So, yep, this isn't trivial, and it's something that needs to be proven separately. Okay, so what do we want to start with?
Assuming you're actually.
Assuming the antecedent. Let x plus y equal x plus z. And we're trying to show that y is in fact equal to z. Okay, now what? What would a junior high kid want to do?
Subtract x equals x.
Subtract x from both sides. What's our subtract axiom?
Axiom 8.
Axiom 8. So somehow we got to use 8 here.
So you're going to find a number added to x that's such that it's 0.
Right, so 2. Then there exists something out there, call it whatever we want. I'll use w again, such that x plus w is equal to 0. That's from axiom 7? 8.
8.
Okay. And so then what do we get? Then w plus x plus y is equal to w plus x plus z. I'm going to start being lazy here. And we now understand that we have associativity, and so we can add these however we want. And so we're not going to start writing parentheses saying, hey, we're going to do it this way. We're going to start getting lazier and lazier here. Because it doesn't matter where we put the parentheses. We can always reorder it so we get the parentheses where we want. And in fact, I'll just put the parentheses where I want. I'll put them where I think it's most telling. So w plus x plus y is equal to w plus x plus z.
So those 0, aren't they?
Yeah, and w plus x is 0. So I get that 0 plus y is equal to 0 plus z. And now we're going to stop using commutativity to swap the order, then add the 0. We're going to make the bold claim that you know that 0 plus y is the same thing as y plus 0 from commutativity, and we don't need to bother doing that step anymore. And so then we get y is equal to z. And we're done. Good? All right. Theorem 4 is x times 0 is 0.
No, speak. Does not feel like it should be theorem. Feels like.
Well, you can derive it from the axiom.
I know.
X times 0 is always 0. Now, this is not given just in the axioms. Right? One of the axioms talks about how 0 behaves with addition. This one talks about how 1 behaves with multiplication. Now we're talking about how 0 behaves with multiplication. And strangely enough, when we multiply by the additive identity, we always get back the additive identity. Very strange.
It's strange.
I know.
At first it's not strange. Then you think about it more and it becomes more strange. Then you think about it more and it becomes not strange again.
Tuition says we should use axiom 9, but I don't know for sure.
So I'm trying to show that x times 0 is equal to 0. Now this one's hard because it's not a implication. Sorry, I didn't write this very correctly. We're trying to show it for all x. X times 0 is equal to 0.
Oh, yeah.
Be more careful. It's not an implication. We're on, or do we start? So I'm going to start with x times 0. So observe, x times 0 is equal to, I'm going to write 0 in a different way. Again, going to assume something we haven't proved yet, but 0 plus 0 is in fact 0.
Oh, it's not.
It's a one-line proof.
Okay.
Anything plus 0 is just that thing.
Yeah.
Oh, that's right.
So it's a one-line proof. Don't think it's too big of a leap for us to make. Right? Now what's this equal to? Notice that.
Oh, we got axiom. 5, isn't it?
Axiom 5. Right.
Is that where we're going?
Yes, yes. So I've already got this inkling in my head. I've somehow got to make axiom 5 come up. Because it's really the only one that gives me this interplay with plus and multiplication. And the only thing I really know about 0 is it's an additive identity. And so my brain is thinking, I've got a multiplication with an additive identity. I somehow need something that's going to interplay with addition and multiplication. And so that's my thought process in trying to get that to show up. And that should give me something to work with. And now, using this, axiom 5 is our distributive property. X times y plus z is x times y plus x times z. And so x times 0 plus 0 is x times 0 plus x times 0.
Well, I feel like we're backwards, right?
Well, yeah, it does seem.
Whoa, we've made a lot of progress. We showed that x times 0 is equal to x times 0 plus x times 0.
Which,
What are we trying to show it's equal to?
0.
0. You can almost use, what was our previous theorem? Left-hand cancellation. You can cancel out the left-hand thing on both sides, and the right-hand thing is equal. If I try to use left-hand cancellation, we're in trouble because there's nothing over there. We want there to somehow be a 0 over there. If we could get a 0 when we do our left-hand cancellation, then we're golden.
so you're saying we can't use theorem 3?
Not yet.
We're so close. We can't have nothing on one side of the equation.
Well, we could.
You could add 0
use
with everything
axiom
and it
7.
itself.
Oh,
You could just add a 0 and it doesn't change it.
yeah.
So rewriting this side, so 2, then x times 0 plus 0, added 0 to that bad boy, made it way bigger, is equal to what we had on the right hand side still, x times 0 plus x times 0. Now we can use our left-hand cancellation, theorem 3. Theorem 3 says that if you have something plus something equal to, if the things in these two positions are the same, you can get rid of them. And the right-hand side things must be the same. So then that gives me that 0 is equal to x times 0. So any number multiplied by 0 is in fact 0. I like that proof because it's a somewhat surprising result that's so easy to show. What was that? Theorem 4, so looking for theorem 5. Theorem 5 is saying that the additive inverse identity is unique. Let's just move the camera. Okay, so theorem 5 is that for all x, there exists, and we scream that there exists, which means that there exists one and only one. There exists one and only one y, such that x plus y is equal to 0. Now notice that this is almost identical to axiom 8 here. The only difference between this and axiom 8 is that explanation point. Axiom 8 says for every x there exists y such that x plus y equals 0. This says for every x there exists a y and only one y such that x plus y equals 0.
Why wouldn't we
Is
just
that
have
explanation
that
point like
as-
a standard thing? Or
Yes, this is very standard notation. This means there exists one and only one.
Okay.
Why would we?
And we did define it in logic. It's just one that it's not used very much, so it was just a kind of a side note. But
Why
I
would
think I
we?
remember that. Sorry.
How do we talk about there being one thing when we don't have a?
a unique. We do not mean one, the member of the real numbers. We mean one as in unique. Now it turns out that those two things are very closely related. That when we mean that something's unique, we mean the cardinality of the set containing it is that number.
Why don't we just make axiom 8 have the explanation?
Because you don't need it. This is already entailed in those axioms. Why would you throw more than you need? Minimalistic here.
Because it communicates clearly.
But we could have, and there would have been nothing wrong with it. But mathematicians want you to have to think. They don't want to just hand that to you. My goodness.
I guess so.
It was kind of machines.
All right, so let's think this through. How am I going to prove that there's one and only one thing that satisfies it? I already know that there is one thing that satisfies it. That's given to us for free. How do I know that there's only one thing that satisfies it?
Could we assume there's two things? And then show how that applies to combination?
Yeah, so if there's not only one thing, how many things would there be?
More than one.
More than one. And if there's more than one, there's at least two. So I'm going to show it's impossible for there to be two things out there that do it. Therefore, there's only one.
Wait, but then
If I know that there is someone in the classroom, and I prove that's impossible for there to even be two people in the classroom, how many people are in the classroom? I know someone's in there, and I prove it's impossible for there to be two.
the one person.
There's only one.
It's true. That's the one way to do it.
So that's what we're going to do. We already know that there's one thing that satisfies this. That's given to us from the axiom. I'm going to show that's impossible for there to be two things that satisfy it. So, assume, by way of contradiction, that there exists both y and I'm going to use y prime. Y prime here is just another variable. I could have used a different symbol like z, w, whatever. We typically use prime when we're saying that the two variables we're talking about are somehow related, and I want to keep that in your mind. So y is one, y prime is another one. So assume by way of contradiction that there exists y and y prime such that x plus y is equal to 0, x plus y prime is equal to 0, comma, and y is in fact different from y prime. So assume that there exists two things out there that are the additive inverse of x, and they are in fact different things, not the same thing. The contradiction I'm going to get is that they're in fact the same thing. With me? Okay, 2. How am I going to get that they're the same thing? What's x plus y?
0. Oh,
What's x plus y prime?
also 0. So it's
So x plus y equals
x plus y prime.
x plus y prime. So then x plus y is equal to, we can substitute equals for equals.
Yeah.
It's a lot of logic.
That's using identity, yes, perfect. And now what can I do?
Oh, you can just subtract x.
Theorem 3, left-hand cancellation rule.
Yeah.
I don't know what subtraction is. I know what left-hand cancellation rule is. That's theorem 3. So that gives me that, which gives me that y is equal to y prime, contradiction. Because we said y is not y prime. And when y is not y prime, y is y prime. So if there exist two different things that have this property, they're the same thing. Contradiction.
Yeah.
All right. Let's see what theorem 6 says. Oh, we're now ready for our definition. Okay. So we haven't gotten to a theory of definition yet. When we get there, one of the things we're going to do is we're going to make it what you call deterministic. We need to show that if you're going to define something, first off, you have to show it's unique. A definition needs to be talking about a thing. And since I showed that an object has a unique additive inverse, I can now define some symbol for that additive inverse.
Okay.
Make sense?
Yeah.
So, our definition here. So definition, I'll call it definition 1. For all x and y, yeah, I guess I'll do that. Negative x equals y. So we are introducing now a new symbol. Never seen it before. So definitions introduce new symbols.
We have to put the dots.
What do I mean when I say negative x equals y? By definition, that means
Wait,
that x plus y is equal to 0. That is our exact definition. What do we mean by negative x? I mean the unique thing such that when you add it to x, you get 0. I proved that there's one and only one thing that has that property. And so now I'm defining it. What is the one and only one thing that when you add to x, you get 0? Negative x. From here on out, that's what negative x means, and that's the name we'll slap on there. We're going to call that the negative symbol. So this is not a primitive. This is now a defined symbol, our first new defined symbol. Well, I guess technically we define some numbers, 2, 3, 4, etc. But those are more side definitions. Okay. Any questions so far about that definition? Colon there is on the side that has the new symbol we're defining. We call that the definiendum, and those the definiends.
You use an equal sign when you define the numbers, and here you use the.
There are two ways, again, we haven't done theory of definition yet, but there's two ways that you can define a new symbol. You can use a logical equivalence, or you can use an equals.
Doesn't matter.
They have different rules for them, and we'll go over exactly what those rules are. So, again, we're jumping the gun to get you comfortable with it before we go over the rigorous theory of definition. Because theory of definition, that's the last part of logic that we haven't done yet. That's logic proper. This technically isn't logic proper. It's just an example of a system using logic. Okay, so now we're ready for, well, before I say that, let's talk about R again. So what did we know about R so far?
They can change it now.
We knew it had a 0, we knew it had a 1, we knew it had a 2, we knew it had a 3, ... But now I also know, since it has a 0, it has a negative 0. Since it has a 1, it has a negative 1. Since it has a 2, it has a negative 2. Dot, dot, dot. Now you might be thinking negative 0, what on earth? Turns out 0 and negative 0 are the same thing, and we'll prove that. So we accidentally listed out the same element twice there. That doesn't matter. But so now we have shown, with this new definition, we now know that all the integers are for sure in R. And so all these symbols, if I ask you the definition of any of them, you should be able to tell it to me. What's the definition of negative 2? It's the additive inverse of 2. What's 2? It's 1 plus 1. What's 1?
It's
Bad question. Don't ask for the definition of 1. It is a primitive. It's an undefined term. It doesn't have a definition. Good? Okay. So now our next definition, or not next definition, our next theorem is that negative x is in fact x. So we define that negative symbol. Our next theorem here, theorem, we're on 6. Theorem 6 is that for all x, negative x is in fact equal to x. That's what we're trying to prove. All right, once again, it's not implication. So our starting point isn't a gimme. So what are we going to do?
By way of contradiction is always the next go-to.
Let's just write the symbol out and see if we can make it look like that thing. So 1. So negative x is equal to what? I got to, without changing it, show that's equal to x, without changing its value. What's the only things we can do to numbers to not change their values?
substitute.
So definition 1 could...
In algebra, over and over again, when we're manipulating expressions without changing the value, we're either adding zeros or multiplying by ones.
Yeah.
Now, this is talking about the additive inverse, negative, right? So that's begging for somehow we want to add zeros onto this in a clever way. So this is equal to negative x plus 0. But can I come up with a clever way of rewriting that 0? That somehow introduces the x symbol.
Yeah.
What's something?
Oh, you can times 0 times x is...
Yeah, but we probably want to stick with addition.
Yeah, never mind.
But that is something. How can I write 0 using x?
You're done.
It's like going back to group theory, we would often replace our e with what?
I forget.
You don't remember replace it with this over and over again?
The inverse of x?
Something together with an inverse.
I kind of want to, well...
Alright. Clock's expired. X plus negative x. That's something that has an x in it. That is just 0.
That's true.
So I got my x symbol to show up.
We've already defined negative x, so that works.
Yeah.
Yep.
What is negative x? It's a unique number such that when you add it to x, you get 0.
You can add 0 as many times as you want.
Okay, so I got negative x is equal to this whole thing. I got my x there, but now I have these two annoying pieces. What do we know about these two annoying pieces?
They're the same.
They're not the same.
Negative x. I see.
What do we know about those two things?
Oh, they're the inverse of each other.
They're inverses of each other. This is a negative of that. What is this number? This is a number such that when you add it to negative x, you get 0. That's what negative x is.
Just get x.
So this is just equal to, write those two together just to try and keep it very clear. Negative x plus negative x plus x. Right? So some number added with its inverse is 0.
That's right.
So that's equal to 0 plus x, which is then equal to x. So there we go. Negative x is just x. Any questions on that? What's next? We're trying to show that -1 times x is equal to negative x. Okay, theorem 7. For all x, we want to show that -1 times x is equal to negative x. Okay, so I'm not sure how I'm going to do this one yet. Maybe I'll scribble some scratch work over here. But the first thing instantly coming to my head is I'm somehow going to want to use the distributive property. I've got additive inverse of 1 being multiplied by an x. This is the additive inverse of something. This I want to somehow get through the distributive property. So here's my idea. We'll see where it goes. So to get a -1 times x through a distributive property, I'm going to start out with -1 times 0 is equal to -1 times, and remember that 0 is the same thing as, maybe I should have started this with just 0. Probably should have done scratch work this side first. So 0 is the same thing as -1 times 0, which is the same thing as -1 times my x plus negative x. You with me? So far I'm thinking that that's going to give me a -1 times an x. That's what I'm thinking. And then this is also equal to, since this is equal to 0, 0 is also the same thing as x plus negative x.
Yeah, makes sense.
So now I probably should have started this over here. This is equal to 0, and this is equal to 0, so this is equal to this. Okay, so let me just rewrite that down here. So what did we get? I got that -1 times x plus negative x is equal to x plus negative x. My motivation there so far was simply trying to get a negative x to show up and something that I know a -1 times x would show up when we did distribution over here. So now let's distribute over here and see what we get. -1 times x is going to be -1 times x plus -1 times negative x, which is equal to x plus negative x. Right?
Let's see.
That's not getting me where I want it to.
Yeah, you're adding -1 times negative x. I don't know how we can do that without first proving the theorem.
Yep. My idea did not work out. Let me do some scratch work to the side really quick. Let's see if I would have tried this approach. -1 times x. Ooh, do. -1 times x plus negative x.
Stand up, cheese table. Oh, meetings.
Yeah.
Doing this all day, all time.
let's see. I know that negative x is equal to x, but that doesn't help me. Because my problem with this approach, I got my -1 times x, but I also got my -1 times negative x. Let me try, maybe I should have done my distribution the other way to get my -1. Maybe I should have thought about x times 1 plus -1. I think this will work better. So, no, I know this is equal to 0, right? So 0 is equal to that, is equal to x times 1 plus x times -1. Okay, and then this is also going to be equal to x plus -x. Okay, yep, that's. So I had the right idea, just distributed the wrong way. Okay, sorry. Let's restart now that I got the scratch work. So on the one hand, I know that 0 is equal to x times 0, right? Anything times 0 is just 0, which is the same thing as x times 1 plus -1, which is equal to x times 1 plus x times -1. I also know that 0 is equal to x plus -x. So I know 0 equals that, and I know 0 equals this. Therefore, I know that equals this. With me? So I know this is equal to that. So then, I have that x times 1 plus x times -1 is equal to x plus -x. Now what is x times 1? Just x. So that's x plus x times -1 is equal to x plus -x. Now what can we do?
We can remove x on both sides.
Yeah, we can use our left-hand cancellation law. So that gives me that, I'm also going to swap the order I write those. So that also gives me that -1 times x is equal to -x, which is what we were after.
How did you come up with the, see, 1, 2, 3, 4, the end equal on the very first line? That one, yeah.
Here to here, distribution. So I knew I was somehow going to have to use distribution in this thing, or at least that was what I was looking to do.
Okay. Yeah.
I just tried distributing over x and -x rather than 1 and plus -1,
Yeah, that makes sense.
which is giving me some terms that I want. Okay, but I think that works. Any questions on that? Hopefully I don't get stuck on any other ones. Quick corollary then. So corollary is something that follows almost for free from a theorem. So we're not going to call this its own separate theorem, just quick corollary. And our corollary is that 0 is equal to -0. So how can I prove that?
Technically using the exact same process.
That's overkill. So 0 is equal to -1 times 0, because anything times 0 is 0. And what is -1 times 0?
-0 by term 7.
Just -0. So there you have it. 0 is in fact equal to -0. They're the same number.
Is there any type of rules that we don't allow -0 to be a thing?
No? It's perfectly fine.
So if we have two symbols that
I just wrote 1.
It's a great point. Yeah.
Okay, so that takes care of Theorem 7. On to Theorem 8. Theorem 8 is negative x times negative y is equal to x times y. So Theorem 8, this one says for all x and y, negative x times negative y is equal to x times y. Sorry, didn't write my dot for times. Multiplying those together. Okay. We have any ideas for that? Ooh, we don't have negative 1 times negative 1 is 1 yet. That's what I was first thinking. Negative x times negative y is equal to x times y.
That might just be a corollary. If we prove this, we can prove the negative 1.
Yeah, I see a way to quickly do it with the 1s though, if we had that first. And I'd be wonder if it'd be easier to do that first. Could you really quick think of a way that this is equal to 1 times 1?
It's
No.
the theorem 6, right? Or no?
No, we don't get that for free. So this is something that we would somehow have to prove. How would I want to get my negative 1 times negative 1? That is the question. So let's see if I can think about a way to do this really quick. Let's see, I know that negative 1, I know that 0 is equal to negative 1 times 1 plus negative 1, right? Which is equal to negative 1 times 1 plus negative 1 times negative 1. But negative 1 times 1 is the same thing as negative 1. So that's equal to negative 1 plus negative 1. Okay, I think that'll work. So there's probably an easy way to do this that I'm just not seeing. I'm seeing how we could do it with this off the bat. So rather than making this a corollary of that, I'm going to make a lemma to proving that. And we'll introduce a lemma. So before Theorem 8, we'll prove that. I'm going to do lemma. Lemma is what you call a quick helper proof. Your author does it after, but it doesn't really matter. Okay, so lemma, I'm going to prove that negative 1 times negative 1 is equal to 1. We won't say 1 times 1, we'll just say 1. All right, so going with exactly what my thinking was, I know that 0 is equal to negative 1 times 0, which is equal to negative 1 times 1 plus negative 1, which then distributing, I get negative 1 times 1 plus negative 1 times negative 1. Why did I even think to do that? I'm just trying to come up with some way to get this symbol to show up. Negative 1 times negative 1. That's the only reason I went down that path, is I was just trying to get this thing. And then I'm just trusting that I'll be able to figure out how to get rid of this down the road.
Okay.
And I also know that 0 is just equal to 1 plus negative 1, right? And now, using this theorem, negative a number is the same thing as negative 1 times that number. So negative a number is the same thing as negative 1 times that number. You guys me? And then I'm just going to swap the order I write those, just to help make everything more appealing, easier to see. So I know that 0 equals this thing, and I know that 0 equals this thing. Therefore, this thing equals this thing. So I know that this, which is negative 1 times 1 plus negative 1 times negative 1, equals this thing. Negative 1 times 1 plus 1. Now what can I do?
You can remove negative 1 times 1.
Left-hand cancellation law. I can cancel those things out, and I'm left with that equals that. So that gives me that negative 1 times negative 1 is equal to 1. So there's our lemma. Now let's go do the theorem, and now that theorem will be easy. It's probably easy some other way that I just wasn't seeing on the fly, and don't want you guys to have to sit there and stare at me think. So the next one we were trying to do is for all x and y, negative x times negative y is equal to x times y. What's my thinking here? We'll factor out the two negative ones here, multiply them together to get 1, and we're left with that. So I've got that. Negative x times negative y is equal to, a negative number is just negative 1 times that number. So this is negative 1 times x, this is negative 1 times y. So this is equal to negative 1 times x plus negative 1, or not plus. Negative 1 times x is replacing negative x. So I'll put parentheses there to help remind us. This is the same as that, times negative 1 times y. This is the same as that. Now, since multiplication is associative and commutative, I can take the negative 1s out and multiply them first. So I can view this as just negative 1 times negative 1 times x times y. Using our lemma up there, negative 1 times negative 1 is 1 times x times y, and 1 times anything is just that thing. So there we have it. Negative x times negative y is the same thing as x times y. Somehow two negatives cancel out each other when you multiply them. So did theorem 8, rather than a corollary, we did a lemma leading up to it. Go ahead.
I feel like we're breaking some rules here because
What rule did it feel like we broke?
it's a law of logic where just because we found a single what's the opposite of generalization?
Specification.
Just because we found a single true specification does not mean that we can apply a generalization by saying all of x. I don't know. Doesn't that kind of indicate there's a problem there, the reasoning?
Well, we can't go from this straight to this. This is a generalized version of that. We found a specific number that satisfies this.
Yeah, but you used a specification to prove the generalization, and I worry if that's breaking a law of logic.
No, it's perfectly fine. We handled the special case. I mean, imagine we did it the other way and we proved this one first.
Well, if you
We didn't have to prove in a general case before we proved for one specific case. If you find a way to prove one specific case first, then you proved one specific case.
exactly.
It would be like if I proved before the Pythagorean theorem, first I proved somehow that with this triangle, if this is 3, this is 4, then this is 5. Special case of the Pythagorean theorem.
Yeah.
If I then specially use that in proving a general Pythagorean theorem, perfectly fine. If I proved it separately and it stands alone by itself. We just have to make sure that I didn't then use the Pythagorean theorem to come back around and try and prove that somehow. So this would be a problem if somehow I tried circling back and using this in establishing that.
No, wait, no.
Because I didn't treat this as a special case of this. I treated this as a standalone proof and then used it to help me prove a more general case. It actually, I mean, this is a weird kind of case for it, but it's actually not that uncommon to do
Specification.
proof of an easy case to help you work towards a hard case. Easy versus hard instead of special versus general. Special versus general is one way that shows up, but handle an easy case to help us with the hard case is somewhat common.
Okay.
But yeah, I think the logic there is completely solid. Or our thinking, I should say. Maybe not the logic, although I think that's solid too.
I mean, you could have easily proven the lemma with theorem 8. I just, the other way around, I have to think about it.
The fact that I had it written the other way means in my notebook, I proved this and then made this follow. I just left my notebook. So I can't quickly see how I proved it. And I proved it the first time I went through logic, which was however many years ago. So it's not like I recently did it. I'm trying to remember what I did.
Well, watching you struggling proving it makes me feel better about me struggling trying to prove it.
Misery loves company.
Yeah.
Let's see. So we're ready for our next definition. What definition number are we on? I think this is just our second one, right? So far we just defined the negative symbol. So definition 2. Now we have our negative symbol. The next thing we're going to define is a new, huh?
Find the numbers.
Oh, I'm not counting those. Those are things that when the author goes through it in the book, he bothers doing. I just like pointing that stuff out. So if you were following along in the book, we're proving what the author goes through. And I'm roughly labeling it the same order he did. Okay. Subtraction. So defining subtraction now. For all x, y, and z, when I say, try and keep the same order he does, x minus y equals z. When I say x minus y equals z, so now this is not a negative symbol. A negative symbol was like a unary operator. It only applies to a single number. This is a binary operator. It's taking two numbers and spitting out a number. So defining a new operation on the numbers, x minus y. What do I mean by x minus y equals z? I'm going to define that to mean that x is equal to y plus z. Let's look at a concrete case. Imagine I told you, I want you to prove that 8 minus 3 equals 5. And I asked you to actually prove that. How would you prove it? You would prove that 8 is equal to 5 plus 3. And that's how you'd actually prove it. So, what do I mean by x minus y equals z? I mean x is equal to y plus z. What do I mean by 8 minus 3 equals 5? I mean 8 is equal to 5 plus 3. Good? So there's our definition. Let's now prove our next theorem. Our next theorem is going to be the way that I like to define subtraction, but not the way the author does. So theorem 9. We're going to prove that for all x and y, we shouldn't have a z. For all x and y, x minus y is the exact same thing as x plus negative y. Now we could have used this as our definition of subtraction. And it says, what do we mean by x minus y? We mean x plus the additive inverse. We could have used that as a definition and proved this as a theorem. Or we could use this as a definition and prove this as a theorem. It's completely logically equivalent. I like this as a definition more, but it's not the one the author uses, so we'll go with the author. Okay, so I'm trying to prove that x minus y is equal to x plus negative y. Alright? So I'm going to say, let x minus y equal whatever it equals, we'll call it z. So z is the thing that x minus y is equal to. I'm trying to show that x plus negative y is also equal to z, and we're done. Right? Okay, so I know x minus y equals z. By definition, what does that give me?
X is equal to z plus y or whatever?
Yeah, that gives me that x is equal to y plus z. Right? Now I'm trying to get that z is equal to x plus negative y. So I need to somehow introduce negative y's into this thing.
Which you can replace the y with the y plus negative y? Is that,
No. Y plus negative y is 0. I can't replace a y with y plus negative y. I'd be replacing y with 0.
Yeah.
But if I don't want to change an equation, what do I have to do?
Add both sides?
Yeah. What should I add to both sides? The thing I want to show up.
Yeah.
I'll just add negative y to both sides. So that gives me that x plus negative y is equal to, also got to add it here, negative y plus z. Now what is negative y plus y?
Zero.
So that gives me that x plus negative y is equal to, negative y plus y is 0. 0 plus z. Or in other words, I've got that x plus negative y is equal to z. So x minus y equals z, and x plus negative y equals z. So just to put it all together, then x minus y is equal to z, but z is also equal to x plus negative y.
This feels more like discrete math than it does algebra. Just this process is extremely blocky. My thought process.
It's extremely what?
It's blocks. There's no continuity of it. Continuity, continuousness. It's just blocky. I don't know. It's interesting.
It is strange how hard it is to think about the most foundational stuff. Right? The very simplest things, it's hard for us to think carefully about, and then there comes a size, enough complexity that it's easy for us to think about it, and we have good intuition for it. And then too much complexity, it gets all hard again. Sometimes the analogy I use is, it's hard for us to reason about strings, it's hard for us to reason about the universe, but you get something that's a meter long, it's just the right size.
Yeah, but this doesn't even take into account the fact that there's a continuity between these numbers.
No, we don't have what gives us continuity
Yeah.
in the strict sense of continuous functions, because that needs a completeness axiom.
Oh. So
There's an axiom missing from that list.
is there? Okay.
Yes. And it's the axiom, so all those axioms, for example, do not give us that the square root of 2 is a real number, as an example. You do not derive that this is an R from those axioms. You need the completeness axiom.
Just one more. Huh?
Just one more. And that one more is what gives you all the strangeness and the coolness of the real numbers. All the calculus comes from the one that we're missing.
Are we gonna teach it to us?
If we did real analysis, it is not an easy one to reason about. And the fact that it gives you these things is, I'll tell you what it is. It's that every set of numbers bounded from above has a least upper bound. That's it. That's the crazy axiom.
Sounds like a proof from topology.
It sounds a lot like things in topology. And you use that axiom in topology when you're talking about topological systems on the real numbers,
Obviously.
or logically equivalent versions of it. It's yep, that's the one that gives you all the strangeness. That's the one that gives you continuity on the real numbers the way that you want to say it. We could still get, in a topological sense, some continuity, but
So it sounds like mathematics is actually built on topology.
topology is a very foundational field of mathematics.
Yeah.
You could view calculus or real analysis as a special case of topology. It's looking at a special topological system. You're looking at the standard topology on the real numbers.
So topology doesn't presuppose any kind of number system?
Now, for topology, you need set theory.
Yeah,
That's it.
That's so cool.
That's it.
Sweet. You teach it.
That is an option for what we do next. We'll see. We'll see who's around and who really wants to do something.
I want to learn freaking linear algebra and vector spaces so damn bad.
That's true.
I'm gonna demand almost.
Well, we'll see what happens, whatever there's the most demand for. Seemed like last time we had the conversation, people were leaning the philosophy route. All right, let's try and get through with a couple more of these. I at least want to introduce division, and then we can call it good. I don't care so much about using the less than symbol. Our next theorem here is that the multiplicative identity, or multiplicative inverses are unique. So theorem 10. So our next theorem here is that for all x, there exists, for all x, if x is not equal to 0, that implies that there exists one and only one y such that x times y is equal to 1. Now once again, notice that this is identical to axiom 9, with the exception of we're saying is unique. And how do we prove this? We are going to prove it identical to how we proved this one, just with timeses instead of pluses. So right here, we're just going to do assume by way of contradiction that there exists two things, we'll call it y and y prime, such that, sorry, I didn't start with, first line is let x such that it's not equal to 0. Okay, so x is something not equal to 0. Now assume by way of contradiction that there exists a y and y prime such that y times x equals 1, y prime times x equals 1, and y is not equal to y prime. Well, I know that y times x is equal to 1 is equal to y prime times x. Right? Ooh, we're kind of stuck. Because I can't just instantly okay, I'm going to do something funny. There's probably another way to do this. I'm going to multiply both sides by y. Because I need to cancel out the x's somehow. But so far I know that this is equal to this, right? So here's where I'm going to do something funny. That gives me that y times x times y. So I multiplied another y over here. I'm going to multiply another y over here. Is equal to y prime times x times y. Now what's x times y equal to?
Oh, yeah.
1. So this gives me that y times 1 is equal to y prime times 1. Anything times 1 is just that thing, so that gives me that y is equal to y prime. Contradiction. So there's one and only one. And now we can define that one and only one thing, similar definition to what we have. Where is it? No, that's subtraction. Sorry, what? Right? Yeah, right. Duh. Right under the theorem where we did it. So now we have a definition almost identical to this. Definition, what number are we on? 3? Definition 3, I can now say follow the exact pattern there. For all x and y, where x is not equal to 0, if x is not equal to 0, then we say that x, and we use this inverse symbol, x inverse equals y if and only if x times y is equal to 1. So same thing as this, we just have to throw in the condition that x isn't 0. So x inverse is y if and only if x times y equals 1. So what is x inverse? It is the one and only thing that I can multiply x by to get 1. And now you can see that this gives us now all our rational numbers. So now, since I knew 2 was in R, I know 2's multiplicative inverse is in R, namely 1/2. And now, since I know 2's in there and 1/2 is in there, well then their sum has to also be in there, which we know is 5/2. And I can do this to get every combination now of rational numbers. And so now, for sure, all the rational numbers are in R. And we can define each rational number however we want it. It's easier to use quotients to do it. So once I define division, then we want to say 3 divided by 5 is really equal to 3 times 5's multiplicative inverse, or 3 times 1/5.
Right.
And then both those are defined, times is defined, so that is a number in reals. So easier with division, but this already shows you that you can do it. Okay, let's see if we can get division, and then we'll call it for today, and next week we'll do a theory of definition. And then decide what we want to do after that. Because we could also do vector spaces in this class if we wanted,
I'll have to say.
and touch on that as an axiomatic system. Just don't want to go too far. Hopefully that for sure isn't too far. Good. Okay. So we defined our multiplicative inverse. I'll skip theorem 10. I'll just write it, but we won't prove it. So theorem 10 is a distributive property with subtraction. And it's that for all x, y, and z, x times y minus z is equal to x times y minus x times z. And the way that you would prove it is basically factor your negatives out as -1 to move it around where you want it, and then put back in the negative symbols by replacing your -1 with negatives again. So theorem 11, where that was theorem 11. Sorry. Now theorem 12 is that for all x, x inverse is equal to x. And this is going to be identical, once again, to how we did this one, basically. So maybe let's try that one really quick. So I got that x inverse. Now, when we were doing the one over here, the way we manipulated it is we added 0 to get where we were trying to go. But since now we're talking about multiplying a multiplicative inverse, rather than adding 0, what are we most likely going to want to do? Multiply by 1. And the special 1 that I'm going to want to multiply, so maybe just be a bit pedantic here. X inverse times 1, so I can multiply by 1, doesn't change anything. But 1, so x inverse times, I'll use square brackets for the 1. 1 is the same thing as x times its inverse. Right? That's what we mean by x inverse. What is x inverse? X inverse equals y if and only if x times y equals 1. Or in other words, x inverse is the unique thing that when you multiply by x, you get 1. That's what x inverse is. So x times x inverse is for sure 1, the same thing that x plus negative x is for sure 0. Going back to group theory, I mean, that's almost exactly the symbols we used in group theory. We said E is equal to x circle x inverse, where inverse just meant any inverse operation, not necessarily multiplication. Okay. So we got that. Now let's just do some regrouping. I'm going to group this together with this and get the x by itself. So I'll write my x first. X times, now I'm going to group these two together. I got x inverse times x inverse. Using associativity and commutativity. You follow that? And what is x inverse times x inverse?
X inverse.
We got something times the inverse of that thing.
How?
I'm going to replace my x inverses here with a different symbol, W. This is the same thing as x times w inverse times w. What is w times w inverse?
Oh, 1. Or-
1.
Yeah.
A number times the inverse of that number is 1. It doesn't matter that I use extra notation as long as it's the exact same symbols. Those symbols are identical to the symbols inside those parentheses. And so this is just the same thing as x times 1. Sorry, this is equal to x times 1, and then x times 1 is obviously just equal to x. So x inverse inverse is equal to x. It's almost identical to what we did when we did the proof here. We added 0, which gave us x and an x inverse in the addition sense, and we grouped the inverse with the inverse inverse to get back 0. Same thinking here. We grouped the inverse with the inverse's inverse to get back 1. Okay. So now, theorem 13, we'll skip. I'm trying to hurry up and get to division. And then division comes after that. Although theorem 13 is interesting, it tells us the interplay between these inverse operations. Theorem 13 is that for all x, the negative of x inverse is the exact same thing as negative x's multiplicative inverse. The additive inverse of the multiplicative inverse is equal to the multiplicative inverse of the additive inverse. But we'll skip that one and go to, I think we're now to the definition. Nope, not yet. We need our left-hand cancellation law for multiplication. So theorem 14 is for all x, y, and z, if x times y is equal to x times z, that gives us that y is equal to z. Right? So for this one, we'll start by just assuming the antecedent. So let x times y equal x times z. I think it has to be where x is not 0. Otherwise, we're in trouble. Yes, and it says where x is not 0. Whoops. So for all x, y, and z, if x is not equal to 0, then our next implication, if x times y is equal to x times z, that gives us y is equal to z. And I could have just added those two together if I wanted, but
That's what I was imagining.
made a choice there. All right, so let x not equal 0 and x times y equal x times z. Since x is not equal to 0, it has a multiplicative inverse. So 2. Then x inverse times x times y is equal to x inverse times x times z. Just multiply both sides by x's multiplicative inverse. What's x times x inverse? 1 and 1. So I'm left with 1 times y is equal to 1 times z. Or in other words, I'm left with y is equal to z. Right? Now our definition of division. So definition, for all x and y where y is not equal to 0, for all x and y, comma, I'm just going to start putting conditions in here. It's a common thing to do rather than making it part of the implication out there. Where y is not 0, we define x divided by y to equal z if and only if x is equal to y times z. So there's our definition now of division. Once again, the same way that we defined subtraction in terms of addition, we define division in terms of multiplication. And so how would you prove something like 15 divided by 3 is equal to 5? The way that you would prove that is you would show that 15 is in fact equal to 3 times 5. That's what it means by definition. By definition, what does it mean to say 15 divided by 3 equals 5? By definition, that means 15 is equal to 3 times 5. That's what it is. So let's do one last theorem using this definition, and then we'll call it good. The one that I like to use as a definition of division, but we'll call it Theorem 15. And we'll prove that for all x and y, where y is not equal to 0, that x divided by y is equal to x times y's multiplicative inverse. That's the way I like to define division, and then prove that this is a theorem that follows from that, but logically equivalent. So here's the last thing we'll prove. So this is going to be similar to how we did it for the addition case. So 1, let z equal x divided by y, whatever it is. So let z equal x divided by y. By definition, what does that give me? What does it mean to say that z is equal to x divided by y?
Z is equal to y times, or x times y inverse.
Well, that's where we want to get. So by definition, we're looking at this one.
X is equal to z times y.
Well, okay, yes, sorry. X is equal to, I'm doing it right as y times z, just keep it in alphabetical order. That's exactly what it means to say, I guess this might be what's throwing you off. I'm going to say x divided by y, whatever that is equal to z. Just keep the exact same order now. Hopefully that cleared it up. Okay, so that means this. That's exactly what it means. So I know that x over y equals z. My goal from here on out is to show that z is also equal to x times y inverse. So I'm going to multiply both sides of this by
Y inverse.
y inverse. So multiply both sides of that by y inverse, and that gives me that x times y inverse is equal to, I'll write the z first here, z times y inverse. Took this side and multiplied by y inverse, took this side and multiplied by y inverse. Change the order around, which is fine. We have commutativity, associativity, we can do all that. Now, what is y times y inverse? 1. So this is equal to x times y inverse equals z, which is what we were after. Okay, so that gets us division, that introduces us to some division. We'll call it there for arithmetic, so next time we'll continue now with logic proper into theory of definition. Got a good taste of a bunch of different axiomatic systems, different theorems, different definitions. This is a good one to do. Lots of terms, lots of definitions, lots of theorems.
Very useful.
Okay, any questions you want recorded? All right. Now you can tell me about